Welcome to ECE410, the snow day lecture. Today is February 9th, 2010. We're going to be talking about sampling. In particular, we're going to consider the setup that we've discussed over the last couple of weeks. I have an analog signal, and that signal is sampled using an ideal continuous to discrete converter to produce samples x of n that are equally spaced in time of the original analog signal. And we're going to consider the case where this analog signal is then sampled, potentially processed, but then reconstructed to produce a new analog signal, y of t. And we'll consider conditions under which y of t equals x of t. We'll derive in a little bit more detail the mathematical expressions that we derived last time. So what we're going to show is that for an analog signal x of t that has a Fourier transform x of omega, that the discrete time signal x of n has a discrete time Fourier transform x of d of omega, which satisfies the following relationship. It's a scaled version of a periodic replication of the analog Fourier transform stretched in frequency so that the spectrum of x of t, it becomes a periodic function with period 2 pi in discrete time frequency little omega. So now we're going to show this a couple of ways. First, let's start by writing x of n, which are our samples of the continuous time waveform. And because those are samples of the continuous time waveform, I can use the inverse continuous time Fourier transform but I can evaluate that at the time n capital T, because I'm evaluating xa of t at time n capital T. So I'm just writing down the continuous time Fourier transform synthesis relation. This is the continuous time Fourier transform synthesis equation. Then now I'm going to make a change of variable. I want to make this expression look like this expression. So I'm going to let the variable omega, capital Omega, equal little omega over capital T. So then d omega will be d omega over capital T. So then this becomes d omega, I'm going to replace with d omega over capital T. So I'll pull that capital T out front. So I have x of a of omega over capital T, and this becomes e to the j omega over capital T nt. The capital T's cancel. This becomes d omega. So let me just rewrite that a little bit cleaner. That's 1 over 2 pi t, the integral of xa of omega over t e to the j omega n d omega. Let me see if I can focus that a little bit better. Okay. So now it's starting to look like this dTft, but it's not quite there yet. I have this integral that goes from minus infinity to infinity, and I've got xa of omega over t e to the j omega n d omega. Now e to the j omega n d omega is periodic with period 2 pi. So I'm going to play a little trick. If this little omega is going from minus infinity to infinity, I could break that little omega going from minus infinity to infinity into a bunch of steps, each step being of length 2 pi. So I'm just going to play a little mathematical trick and write this as 1 over 2 pi t. And I'll write this now as a sum of a bunch of integrals, each of which is only length 2 pi. I'm running out of page room here. I can cheat a little bit and bring in a little extra paper from the next page. So what did I do? I took this integral that went from minus infinity to infinity d omega. It's still going from minus infinity to infinity d omega, but it's doing it in chunks of length 2 pi, where I've just shifted little omega by 2 pi. So I'll go from 0 to 2 pi, that's the k equals 0 term. Then when k equals 1, it goes from 2 pi to 4 pi. Then when k equals 2, it goes from 4 pi to 6 pi, and so forth. So k spanning from minus infinity to infinity, this integral then captures the same as this integral, the same region as that integral. So now what I can do is I can interchange the order of integration and summation. And I can rewrite this as 1 over 2 pi times the integral from 0 to 2 pi of something, and that something is 1 over t, the sum from k equals minus infinity to infinity, of x of a of omega plus 2 pi k over t times e to the j omega n d omega. Okay, so now we're there. What do I have here? I've got 1 over 2 pi times the integral from 0 to 2 pi of something times e to the j omega n d omega, and that equals, from our definition here, x of n. So whatever is inside here must be x of d of omega by the definition of the discrete time Fourier transform. So therefore we've just shown that x of d of omega must equal 1 over t, the sum from k equals minus infinity to infinity, of xa of omega plus 2 pi